All right, so let's continue where we left off. As a quick reminder, we have put together our modeling data set, which we're calling Office DF. That has 186 rows, one per episode of the show. And in addition to the metadata that already came with the from the package, we have calculated a few other things. For example, we have indicator variables for whether the show was potentially themed around Halloween, Valentine's Day, or Christmas. These we decided based on whether these words appeared in the script of those particular episodes. We have an indicator variable called Michael, which basically tells us whether Michael Scott was on the show or not. And then we also have 4 numerical variables, which are proportions, so values between 0 and 1, that tell us the proportion of the lines that were spoken by the characters Jim, Pam, Michael, or Dwight. So this is our modeling data that we're going to work with. So in the previous video, we've put it together. And so our first task now is going to be to split this data into training and testing. So I've set a seed here. And the first thing that I'm going to do is to set my split. Usually I name this something split, in this case office split. And the function that I'm going to use for that is initial split, and I'm going to apply that to the data frame that we constructed. Remember that in initial split, our default proportion for the training versus testing distribution is so 3/4 for training and 1/4 for testing, and we're okay with that. So we're going to leave it at that. So we can actually run this. If you're curious, let's take a look to see what this object looks like. So it basically tells me the distribution for analysis, assess, or and total. So that would be like the training and testing. And from this, we can extract, let's say office train is going to be training of the split object, and office test is going to be testing of the split object. And so let's go ahead and run these as well. So now in my environment, I have the test and train data sets, 140 rows for training and 46 rows for testing. And we have these with a particular seed. So when we knit our document, we're always going to get the same random sample. We can then specify a regression model. We're trying to predict the outcome, which is numeric, the IMDB rating. So we're going to use a linear regression. So we can call this office mod, and that's going to be a linear regression is the model we specify, and then we set our engine to be linear model. So we can take a look to see what this is saying. So linear regression model specification, and our computational engine is LM. So the next exercise is asking us to create a recipe that updates the role of the episode name, the role of the variable episode name to not be a predictor. So that's going to be an identifier variable. Removes air date as a predictor. Remember, we're trying to capture any sort of kind of date-like information from the variables Halloween, Valentine's Day, or Christmas. And then removes all zero variance predictors as well. So let's go ahead and do that. We're going to set up our recipe. We start with the recipe function, which takes a formula. So we're going to say IMDB rating is our response variable versus everything else in the data set. And the data set that we are going to use to figure out how this recipe is to be applied is the training data set. So we're not actually applying the recipe yet, but we're setting it. So it said to change the role. So that's going to be the update role function of the episode name variable. And the new role that we're going to give it is ID. So we could, remember, give it really any character string, but predictor and outcome are special words that actually mean something here in terms of the role. So I'm going to call it ID here. And it says to remove air date. You might be wondering, why is air date here anyway? We didn't actually use it for anything. At the very end of this application exercise, we're going to compare the model that we're building to the one we built in the previous video where we introduced cross-validation. So that's why we're keeping it around, because we're going to use it for a different model that we're comparing it to. But for this model, we're not using it. So I'm removing that. And then let's see, if we have any categorical variables, we would want them to be made dummy variables, except not the episode name, because we're basically we're not going to use that as a predictor. And then finally, step ZV for removing zero variance variables that have zero variance in them from our model. So let's go ahead. So this is our recipe. That looks good. And let's go ahead. So the step dummy is going to be applied to things like the Halloween, Christmas, Michael, stuff like that. Let's go ahead and save this as Office for a recipe. All right, so now we have our recipe saved. And finally, we're asked to build a workflow for fitting the model specified earlier and using the recipe you developed to pre-process the data. So let's build a workflow. We usually name these W flow. So for a workflow, we initiate a workflow with the workflow function, and then we add model. So our model was called Office Mod, and then we also add recipe, and that was called Office Rec. So let's go ahead and run that to see if it has everything we want. We have a preprocessor recipe with 3 steps. We're using a linear regression model, and our computational engine is LM. So this looks like everything that we have specified so far, which means we can finally fit our model. So again, a lot of upfront cost to get there, but we're going to be able to reap the benefits of this when we are doing things like cross-validation or applying the same recipe in the workflow to our testing data as well. So we can fit the model. We'll call that Office Fit. So start with the model and do a fit where data is the training data set. Let's go ahead and take a look at this output. I'm going to do tidy and print it out. All right, so let's take a look at what's happening here. We have some positive and some negative slope estimates here. So we can start with things like maybe total vote. Total votes has a positive slope. So basically what that number is telling us is that for each additional vote, the episode, for each additional vote on IMDB, the model predicts the IMDB score to be higher on average by 0.000386. So that's a really, really small number. But remember that the total votes variable ranges from like 0 to 8,000. So a single vote difference is obviously not going to make a very big difference. Other things we're seeing, it looks like Lines Jim has a positive slope and Lines Pam has a negative slope. So there could be one of two things going on here. It could in fact be a real thing that episodes where Jim talks more are likely to get more highly rated on average, all else held constant. Remember, we're keeping everything else constant compared to if it was an episode where Pam talks more. But another thing that might be happening is that if you know anything about the show, Jim and Pam are, well, they're in love and they're constantly talking to each other. So they're chit-chatting a lot. So chances are an episode where Jim talks more but Pam doesn't talk more is probably not happening a lot. So these are not necessarily independent variables. So it is possible that these coefficient estimates are not very reliable due to potential collinearity, what we call collinearity between these variables. That is, that we are expecting our predictors to be independent of each other so that we can say things like, as X changes while everything else is held constant, but it's possible that's not the case here. Here for Michael, we have a positive slope. So what we're seeing there is if Michael is in the show, so we would expect the score to be higher by 0.5, all else held constant. That might be something I buy a little bit more, especially considering the very first box plot we had looked at with these data, that in fact earlier seasons seemed on average to be rated higher. And then we're also seeing effects of like negative slopes for things like Halloween and Valentine, which is surprising to me. I thought some of those episodes were funny. But then for Christmas, we have positive. So again, we're not necessarily going to dig too deep into these, especially because we haven't really done any checks in terms of collinearity between these variables. But it's still interesting to kind of take a look to see if these coefficients make sense. All right, finally, we're asked, well, you fit a model, you know, we kind of just came up with these variables and tried to fit a model, but how does this model actually perform? Does it actually do a good job predicting our outcome variable? And so we're working with our training data, and what we're going to do is to perform, in this case, 5-fold cross-validation. So how do we do that? We start with our office data sets. Office train, and we're going to say 5-fold cross-validation. Let's go ahead and set our seed. So these are our folds. Our splits are 112 to 28. So it's the same, 140 is divisible by 5. So we're able to get the same number distribution for each of our folds. And what we're going to do is we're going to, again, start with our workflow. But this time, instead of just fitting a single model, what we're doing is we're fitting resamples. So you can see, and we're fitting it to the folds as opposed to just the training data. So we've already built our workflow that knows our model and that knows our recipes for pre-processing. And we're getting to leverage that here when we're doing cross-validation, when we're going to be fitting these models 5 times. To 4/5 of our data as part of our cross-validation step. And the code is very similar to what we did before. Start with the workflow. Instead of fit, it's fit resamples. And instead of a single training data, it is folds. So let's go ahead and do that. And remember that this step might take just a little bit of time just because we're actually fitting multiple models there. And then we can go ahead and collect the metrics. All right, so we're seeing an RMSE of 0.384, and we're seeing an R-squared of 0.564. So 56.4% of the variability in IMDB scores can be explained using this model, and our RMSE is 0.384. So we talked about how that number alone is not necessarily very meaningful, but if we compare it to the range of our, let's say, office train IMDB rating, so our IMDB ratings in this data set range from 7 to 9.7. So almost a 3-point range there. And our RMSE is only 0.384, so a lot smaller than the range of our data. So our average prediction error seems small compared to the value, the range of values our data can take, which seems somewhat promising. But again, in isolation, that number may not be very meaningful. What we really want to use this number for is to compare 2 models to each other. So what we want to do here is, now that we have 2 candidate models, one that we've developed here in the application exercise and one we had developed earlier when we first introduced cross-validation, we can now use these models to apply them to our testing data and actually compare performance metrics to see which one is doing better. So let's go ahead and do that. So we want to, it says, use your model to make predictions for the testing data and calculate the RMSE. Also use the model developed in the cross-validation lesson to make predictions for the testing data and calculate the RMSE as well. And we're asked which model did a better job in predicting IMDb scores for the testing data. So how do we actually do this? We have, in order to do our prediction, we would use the predict function. The model we're using is Office Fit, and the data set that we're applying it to is Office Test. So that's like our new data. And let's go ahead and call this Office Test Pred. So this has our predictions. And if we take a look at this, that basically has our predicted values, but in isolation, they're not very informative. So what I'm going to do is I'm going to bind these with columns from the Office Test data set, where I select the IMDB rating and the episode name. And let's take a look at that again. So now in one data frame, I have my Y hats, which is my prediction column, the .pred, and I have my observed Ys, which is my IMDB rating. So I can see how off I am. So for example, for the episode called The Alliance, 8.1 is the observed score and 8.48 is what the model predicted for us. So there the prediction error would be 0.38. But again, we don't really want to use just the prediction error on its own. We want to calculate the root mean squared error. We're going to say that calculate the root mean square error based on this data set that we just created. Our truth is the IMDB rating column, and our estimate is the .pred column. So we can see that 0.404 is the RMSE for the testing data, a little bit higher than what we saw with the training data, which is absolutely expected because that's the data set that we had trained the models on in the first place, but not too much higher. And then what I've done here is I've actually included the information from the model that we fit in the original video about cross-validation, where this was the one, if you remember, where we take a look at the air date, but actually take the month out and use that as a categorical variable or a factor variable in our model. So we have all of that information. We can take a look at kind of how the model is fit. We can take a look at the results of that. But what I'm going to do is I'm going to copy and paste the code that I developed just now for calculating the RMSE for the old model. And here we are going to say that instead of using Office Fit, we want to use Office Fit Old. And I'll give this qualifier suffix called old as well. And then let's do this. So let's go ahead and run this to make sure we are in fact getting a different number. So what I'm going to do at this point is knit this document once, right? We've been running the code interactively a little bit all over the place. And so what I want to do here real quickly is to run everything once, and so that we can take a look at our results. Let's make this a little bit wider. Okay, scroll down, and I'm going to go all the way to the bottom to exercise 10, which asked us to do our calculations for the two models. So our RMSE for the testing data with the new model is 0.444. And our RMSE for the testing data, it's the same testing data that we're working with, for the old model is 0.498. Remember that RMSE is root mean squared error, in other words, the average prediction error. So in this case, what we have is that our RMSE is lower for our newer model, where we had this additional feature engineering done to get things like you know, who was speaking more, and whether it was Halloween episode or whatever. So it looks like potentially it paid off. And so because we were actually able to reduce our RMSE. So if, for example, you had these two models, one of them built by you and one of them by a friend, and you wanted to pick one of them and wanted to do a better job at predicting the IMDb scores, the newer model is probably what you would want to go with, because even on the testing set, it is actually giving better predictive results.